Welcome back. In this video, we're going to go through a couple more trig equations, yet more trig equations, but these ones got a couple of extra tricks to them. So let's have a look at them, because these sorts of things can pop up as sort of more challenging questions on exams. And if you've seen them, then obviously you're a chance to kind of get them right when you see them again. This one here, there's a little bit more going on than our normal sort of trig equations, because we've got a sine x, a cos x, and another cos x throughout the equation. What we might look to do is actually, I guess, rearrange the equation to begin with. One thing that you've got to be a little bit careful of is it looks like dividing by cos x could be a good idea here. Only problem is that we know in maths we're not allowed to divide by 0, and cos x equals 0 is actually a solution to this equation. You can see that if cos of x was 0, the equation would actually be solved, and therefore we can't divide by cos x because it's possible that cos x equals 0. So next thing we can look to do is get everything to one side. I'm going to put some brackets around these x's because that's how they should be written anyway. So I'm going to subtract the cos x on the right, from the right hand side over to the left hand side. And just see if that looks any better. Now, what you can see here is we've got an equation with two terms in it, equals 0 on the right hand side. As much as it doesn't look like the sort of equation we'd normally factorize, there is a common factor in both terms, and that common factor is cos x. So if we take that factor out, we can rewrite the equation as cos of x. Just because we've got so many brackets going on, we use square brackets there. What we'd be left with is root 2 sine x minus 1 inside the bracket. And from what we know about the null factor law, if you've got one thing times another thing equals 0, well, that just means that either the first thing equals 0, in other words, cos x equals 0, or the second thing that we're multiplying by has to equal 0, which means root 2 sine of x minus 1 equals 0. All right, and we're just going to go on and solve both of these, paying attention to the domain which was given in the question of x is between 0 and 2 pi, not included. All right, so cos x equals 0, that kind of looks easier than normal, but it's a bit different to what we're used to. It might kind of take you a second to realize what we've got to do is go back to the unit circle. Remember that we read sine off the y-axis, sine x, and cos x, I nearly got that the wrong way around, off the x-axis. So if cos x equals 0, really means we're at the points around the unit circle where the x value, the x-axis value, is 0, and that's up here and down here. Okay, so that will be x equals pi on 2, and x equals 3 pi on 2. From the second equation, I might just do this to split it up. We've solved one like this in the previous example. We'd have to add the 1 over, divide by root 2. We get sine x equals 1 over root 2. Think of the triangle that has the 1s and the root 2s in it. That's going to be the triangle where the angle's pi on 4. And so x equals pi on 4 would be our, I guess, base angle, our first quadrant angle. It's sine x equals positive number, and we know that sine is positive in the first and fourth quadrant, so we've actually got our first quadrant answer already. Second quadrant answer would be x equals pi minus the first quadrant angle, so pi minus pi on 4, which will be 3 pi on 4. Now, so far we've got 1, 2, 3 solutions, and they're actually all within this domain of 0 to 2 pi. What we do need to check is if we can find any further solutions. So for both equations, cos of x equals 0 and sine of x equals 1 on root 2, for both equations the period is 2 pi over 1, which is just 2 pi. Okay, so let's think about this, and we might even again think of it, we've got some over 2s and some over 4s, so you might want to call it 4 pi over 2 or 8 pi over 4. So in our heads, let's think about it. If we do pi on 2 plus 4 pi on 2, that would give us 5 pi on 2, which is like 2.5 lots of pi, so too big outside the domain. If we subtract the period, if we subtract 2 pi from either of these answers, well, we're going to get negatives, so adding or subtracting to these two, no good. X equals pi on 4, actually I think I missed that one before, we've got 4 solutions, haven't we? X equals pi on 4, let's see, if we add the period to that, if we add 8 pi on 4, no, that's going to be too far. If we add 8 pi on 4 to 3 pi on 4, 11 pi on 4, again, that's too big. What about if we subtract? No, both of them are going to become negative. So actually these 4 answers are our final 4 answers. And so I'm going to write them a bit more clearly just down the bottom. We had pi on 4, pi on 2, 3 pi on 4, and 3 pi on 2 as our final answers.